In this last video, we're going to talk about one of the delicate questions that's left, which is how do you decide which series test you want to use to solve a question about convergence of a series. So we're going to take a look at some examples and I'll try to break down what my thought process is. But at the end of the day, you're going to learn this by practice and by intuition, by looking at these things and sort of picking up on the patterns and learning to sort of identify recurring features. Okay, so let's choose a convergence test. So before we can even begin to think about deciding which kind of test we want to use, let's think about all the tests that we have. So we have the divergence test. This applies to all series. And then we have these four tests here, the integral test, the direct and limit comparison tests. So that's technically two tests, but I'm lumping them together because they work in similar circumstances. We have a ratio test and we have a root test. And these are for positive series, or a series of positive terms. So these really answer the question about absolute convergence. We have one test here that's the alternating series test, and that applies only to alternating series, obviously. And this one is useful for conditional convergence. This guy up here, the divergence test, applies to everything. So it's super general, super widely applicable. Unfortunately, it's not super powerful, right? But I do recommend that we use the divergence test first on anything we want to look at, and then afterwards there's going to be a little bit of a sneakiness involved in deciding which of these series apply, which of these four middle ones that are relevant for the question of absolute convergence or convergence, straight up convergence if we're looking at a series with positive terms. Okay, and then I should mention there's sort of a few little side things that are not exactly tests. Right on the side we kind of have the method of telescoping series, if we're lucky enough to be able to view a series as a telescoping series. And of course we have the named series. So what do I mean by that? I mean the geometric series and the p-series. Right, those are series with names, and those are going to be fantastic. Right? These are going to be the benchmarks by which we measure all the other series. Okay, so the question we're usually asked is, does my series converge absolutely? Does it converge conditionally? Or does it converge not at all? And so this is just sort of a general guideline I'm going to give you, but your practice will, on many examples, will give you some intuition and some feeling for what methods are likely to work on what problems. Okay, so the procedure that I tend to do is, the first thing I do is I check the divergence test, often directly in my head. Right, so this is often in my head without writing anything down. If you're able to do it in your head, that's really good. If not, do it on your scratch paper and see if it gives you something. If it does, great. Most of the time, it's useless. Right? Most of the time, it tells you nothing. But when it tells you something, you win. Then the next question is the series obviously a telescoping series? If it's obviously telescoping, you're in business. If it's not obviously telescoping, it may still be telescoping. But if you don't see it right away, just proceed forward anyway. And then the next step is to look at the series of the absolute values. Right? This is to answer the question about absolute convergence. If it kind of looks like a p-series, you want to do a direct or a limit comparison test. I would say that the limit comparison test is the most useful if your ak looks like a rational function in k. Right? So something with powers of k on top and powers of k on the bottom. If you have something that has some k factorial junk in it, I would recommend the ratio test. If it has junk to the power k, then you want to use either the ratio or the root test. Now let me point out, if root or ratio is inconclusive, right, so that means that quantity we called r, big R, was equal to 1, don't bother trying the other one. So if big R is 1 for the root test, it's going to be big R equal to 1 for the ratio test, right? So move on to a different thing. Don't try ratio or root. You have to move on. Okay, so that's a useful thing to remember, that ratio and root are about equally powerful. Then if you really can't come up with anything else, right, you can't figure out a direct or a limit comparison, ratio or root don't actually help you out, they're inconclusive. If nothing else works, try for the interval test. Okay, and then if it converges, you're done. It means it converges absolutely. And the series has different signs in it, right? So some of the terms are positive and some are negative. You get to check the alternating series test, right? Alternating series test, super easy to check, easy to work with. The thing is, it requires an alternating series, and most series you're going to see are not alternating. Sometimes they are, often they're not. Okay, so here are some example problems from the book. This first one has this minus 1 to the k times 2 plus 1 over k squared to the power k. Okay, so we see this power k up here. We're tempted to do something like the ratio test or the root test. But before we get ahead of ourselves, let's remember the divergence test. So the divergence test, we take the limit as k goes to infinity of these terms. And here we see something that looks like, right, as k goes to infinity, the term inside the brackets here converges to 2, and it's going to the kth power. So this whole thing is going to plus infinity, so it diverges. Okay, the second series that I have here looks very similar, but now we have the sum from k equals 1 to infinity minus 1 to the k, so it's alternating, times 2 over k squared, whole thing to the power k. Well, here we can use either the ratio or the root test. I'm going to propose the root test. And here we're going to see that the root test is going to have, right, we're going to throw away the minus sign. We're going to take the kth root of this. So we're going to get 2 over k squared. And we're going to take the limit of that as k goes to infinity. So our root test here gives us 0, so this converges absolutely. And then, good, so the next series we have is sum from k equals 3 to infinity of this 2 over k squared minus k minus 2. Okay, that one checks out on the divergence test, right? The terms go to 0 as k goes to infinity. We look at that and we say, well, it looks more or less like 2 over k squared. So we do limit comparison. Limit comparison with 1 over k squared. This converges, it's a p-series. And if you go and calculate the limit, you'll see that you end up with a limit of 2 as the ratio of this term to that term. So limit comparison is going to say that this guy converges because 1 over k squared converges. Okay, so now let's look at this last one here on this page. we have sum from k equals 3 to infinity of 1 over k times the natural log of k to the 7th power. So that one's looking pretty hairy. We quickly do the divergence test. As k goes to infinity, that denominator is going to infinity, so this thing, right, the divergence test, inconclusive. Then the next thing we want to look at is, can we think of a reasonable comparison or limit comparison test on this? And unfortunately, I cannot. I happen to know that ratio and root do not do well on these things that look like they have powers of k and natural logs. So the proposal I would have would be to use the integral test. And a hopeful thing that makes us feel good about using the integral test is that we're going to have to integrate from here from 3 to infinity of 1 over x natural log of x to the 7th power. And that just is screaming for a u substitution, right? So here we want u is natural log of x, du is 1 over x dx. And so our integral over there becomes integral from natural log of 3 to infinity of 1 over u to the 7th du, and then you can check that this converges. Right, so I've skipped some steps here. The point is just to illustrate the thought process. Okay, let's do a couple more examples of this nature. So here I have 100 to the k over k factorial times k squared. This thing, right, that screams out ratio test. This guy right here is a little bit tricky, but here I'm going to recommend that he also we look at with something like the ratio test. I would recommend the ratio test because this denominator looks like square root of 2 to the power k, so that means that's 2 to the power k over 2, or in other words, we can think of it as root 2 to the power k. And then this thing is going to be bigger than that, so we could actually, or the other option, right, or we could do comparison with the series 1 over root 2 to the power k. Right, that's another candidate that we could have. And this guy, of course, converges because it's a geometric series. Right, so that's, for this one, what we could do. Let me illustrate how the ratio test would go on that. Right, that gives us r is going to be the limit. We take the absolute values of these things. So we're going to take the k plus first term and we're going to divide by the kth term. So that's going to give us something that looks like a square root of 2 to the k plus natural log of k over 2 to the k plus 1 plus natural log of k plus 1. So that's the limit as k goes to infinity. We can forcibly factor out this 2 to the k over 2 to the k plus 1, right? That's sort of one of my favorite tricks. We can write this as 2 to the k times 1 plus natural log over 2 to the k. And then down here we get 2 to the k plus 1 times 1 plus natural log of k plus 1 divided by 2 to the k plus 1. And, okay, either using L'Hopital's rule or just knowing it, right, natural log of k grows more slowly than this 2 to the k, So that guy goes to 0, and that guy goes to 0, and that limit is equal to 1 over root 2, which is less than 1. Right, so this series right here converges in one of two ways. We can either do the slightly painful ratio test, or we can do a comparison test, a direct comparison test with this guy. Okay, that leaves us this last example where we have the inverse tangent of 2k minus inverse tangent of 2k minus 2. And this one also has two attacks that are reasonable. One of them is we look at this and we say, hey, that looks an awful lot like a telescoping series. And it is. The other way we can attack this is we can look at it and we can decide to just brute force attack it using the integral test. And for that one, you're going to need to know what the integral is of tan inverse of x dx. You can look that up if you have access to integral tables, or you can just go ahead and figure it out by integrating by parts and carrying through. That's a little bit painful, but the telescoping series way is pretty straightforward. So that one, right, I'll leave to you to figure out, and we can talk about it in class if you have questions about that one.